The gargoyles generally being made out of limestone or marble are attacked by the sulfuric acid. And if you'd go look at those things today, you'd find that they're deteriorated. They have been broken down. They're washed away. You get big rivulets that are carved in the faces of some of the statues because of the acid rain that washes over them. Now, this is corrosion. The action that's going on is corrosion. It's a surface deterioration. In the university where I work, when I went there, which was a long time ago, about 40 years ago, the columns on the building that I am housed in were made of marble, and they were nice and slick and shiny, and they were smooth as glass. And today they look like they're made out of sandstone, and they're rough and all beat up for the same reason, and it's a atmospheric corrosive effect. Now, this is to compare it or to distinguish it from erosion, which is going to be a mechanical deterioration in the surface of the material. Well, you might argue and say it's possible to get corrosion inside of a material, but the surface that I am describing now is anything that's exposed to an atmosphere. So if you get a crack that's going down in a material and the atmosphere is able to get down in the crack, we still call this the surface of the material. Well, let's look at what is considered to be by the people working in corrosion and in electrochemistry, or in the particular field that is associated closely with corrosion. Let's look at, first of all, the mechanism that they like to use to describe the total process of corrosion. And we do this by looking at the first slide, in which we see that in their view of corrosion, and we will examine their view, so-called, in a moment, but in this particular view of corrosion, we are always going to have an aqueous solution involved in the corrosive effect. And so if we have this aqueous solution, and the aqueous solution now is going to be defined as, or the solution, it doesn't really have to be aqueous, but it has to be a solution in which we can have ions of a material available. It is very difficult to get an aqueous solution that doesn't have ionization occurring in it, and so almost any aqueous solution is an electrolyte. In this particular case, we immerse in it a metal, and this is a ferrous-based metal. And what's going to happen here is we are going to ionize the iron. The iron is going to go in solution, if you please, or it's going to break away, give up 2 electrons. The 2 electrons are going to be left behind in the metal now, and the iron, the ferrous ion, is going to appear in the solution. We are interested in what's going to happen now to that ferrous ion and what's going to happen to the electrons that are stripped off of it to cause it to ionize. But the model that's shown here is, of course, exaggerated, but it shows that when the iron leaves the surface, then it actually disturbs the surface or deteriorates the surface, and this is corrosion. Well, in the next slide, we see that water itself is always going to be ionized, and what we're going to have is hydrogen ions and hydroxyl ions, or the radical OH and H in the water. That is, H2O in itself is going to tend to ionize. And so the solution that we are going to put the iron ion into is always going to look like this. So that if we then examine what's going to happen, if we have a metal that's receiving the electrons now, not giving up the electrons, that is to say, if we've connected electrodes so we get the electrons coming in here, what can really happen is the hydrogen ions that are in the solution, which would appear here, will gather up electrons from the metal and become a hydrogen molecule, and that will float on off in the water. So if we can supply electrons to the ionized water, this is what we would expect to happen. Well, in the next slide, we see that we are now back in the good old field of metallurgy, and we know we're going to have crystals, right? We can't get away from these crystals. In fact, we can't get away from this crystalline world at all in anything. I love to remind people that that they're locked in. You can't escape this world. If you're in a plastered room, a concrete floor, a metal roof over your head with metal beams supporting you, you're surrounded by metal crystals. The plaster, the concrete, everything is crystalline. Of course, the metal is metallic crystals. When you fly in an airplane, you go squirting across the sky in a cocoon of metal crystals always. So anytime we're going to talk about these metals, unless we talk about that very unusual, specific, particular class that's called amorphous metals that we talked about before, unless we have those unusual glasses, metal glasses, we are always going to have crystals of some size. So if we look at the slide now, we find that here we have a crystal, and it's this crystal and that crystal. The crystals are exactly the same chemically, but they're different in their orientation. The susceptibility of corrosion of one face of this crystal compared with a different face in the same crystal would be different, except we only have one face of the crystal exposed, and in the adjoining crystal we have a different face of the crystal exposed. And these crystals will set themselves up as a little battery. We will have an anode and we will have a cathode. And in this particular process, what we're going to do is corrode the anode. That means an ion of the metal that's here is going to go into solution. And what will really happen now is the electrons that flowed into the anode will pass into the cathode and meet the hydrogen that is ionized in the water and develop hydrogen bubbles on the surface. And those hydrogen bubbles on the surface are like a plating on the surface, and no longer can the hydrogen ions that are in the solution get to the electrons that are being gathered in the cathode, and so the process will stop. So we have passivated or built a passive film on the material with the hydrogen. Well, what will really happen now is if we have an excessive amount of oxygen in the water, we find that the oxygen in the water will combine with the hydrogen molecules that are on the surface and turn back to water. So we can take two of these things and combine them with this, and we'll take one of these and combine with two of these, and we'll get H2O, and we can do away with this passive film that's on the surface by oxidation now, an oxidation reaction, if we have oxygen in the water. But do you remember when we were way back there in our lessons talking about doing things like solidification, and we talked about the solidification of water, where the water turned to ice at a low temperature and burped out the air that it had dissolved, and we said water will dissolve 20 cc's of air per liter of water. Water has a tremendous solubility for air, and so we always have oxygen available in the water to do that depassivation, to take the hydrogen film away from the surface, and as soon as we strip it off, then we can have corrosion to continue in the process. If we look then at the requirements for corrosion of metals, what we're going to have is an anode in the metal. We're going to have an electrical connection between the anode and the cathode. We have to have a path now that the electrons can flow in, and we're going to have a cathode. And we're going to have an electrolyte in the material, and if we have these things, then corrosion will continue, as long as we don't passivate the material, and in other words, as long as we can enable the passive film to be stripped off. Well, seeing that, I think you can understand that if we had a zinc copper battery, or let's say just a simple cell, a battery that looked like this, then we have an anode, let's say like zinc, and we'd have a cathode, let's say like copper, and we would find that actually the zinc will corrode preferentially to the copper. And we say that the current flows from the anode to the cathode in the cell itself, and from the cathode to the anode outside. So actually, the connection that we have in the battery the connection that we have on the outside, the current flows a little bit opposite the way most people conceive it to flow. But this is the way, let's say, aqueous battery, a battery like a copper zinc battery, or for that matter, lead oxide or sulfuric acid battery that you might have in your car. Any battery works by the same general principle. In the next slide, we see that we have what's called a dry cell battery. And in this particular case, now we're going to have a zinc casing on the outside of the battery. And that is going to serve as the anode. And what we really have is graphite on the inside, which is virtually non-attacked ever by the material. The anode in this particular case is going to be causing the material to anodize or to go into this particular solution, except the solution is just moist ammonium chloride. That is, we don't have to have a fluid material. We can have a pasty material, or we have a fluid with a very, very high viscosity, and we don't have to just depend upon water, that is H2O, in the ionization of the materials. We can have all sorts of electrolytes. So long as we can develop ionization and an ionization potential in the material, then we can get an electrolytic effect, and we're going to get corrosion.
Removing carbon from stainless steel produces a ductile material at room temperature. Even plastic deformation will not transform the austenite to martensite. 3 types of stainless steel exist: austenitic 300 series, martensitic and ferritic 400 series. In a broad sense, corrosion is the electrochemical deterioration of a material's surface. By contrast, erosion is a mechanical deterioration of the surface. Metal grains act as anode and cathode in a corrosion reaction based on their crystallographic orientation.
I think that it doesn't require much imagination at this point now to say, hey, I know a good way to stop all of this. Because if I could impose or superimpose on top of this current that's trying to flow, and the flow of the current is essential now for progressive corrosion, if I could buck a current against that one so I would have no current flowing, if I could set a system up so I could buck that current, then I could effectively say, I'm not going to have any current to flow, and therefore I won't have any corrosion. Well, you will see that we sort of do this sort of thing a little later on, but a gentleman by the name of Courbet generated a diagram to show that particular effect, except he found out that what really happens is that it is greatly dependent upon the pH of the solution. But there's something called a Courbet diagram that the electrochemists rely on tremendously, and it's shown in the next slide. And in this particular slide we see that we have a plot of the electrochemical potential, that is the voltage that we're going to impose on a material, and this voltage is going to be either a positive or a negative voltage relative to the material. That is, we can help it. We can impress a voltage on it that will help the flow, or we can impress a voltage on it that will oppose the flow. And then if we look at this as a function of the pH of the material, where we go from a pH of, say, something very low here to something that's very high, and zero potential being right there. And what we know is a standard potential pH being about 7, being in this region right here. Now what it really says is that by imposing electrochemical potential on a material, we can cause it to become immune. That is, we can sort of stop it from corroding just by bucking it out with this other current. Or we can get a condition where we have active corrosion. Actually, it's in 2 fields you see here. There's a field over here that's corrosion, and there's a field over there that's corrosion at these particular very low pHs, very high pHs. But at